Alright, welcome back to our second last lesson for this week, and this is on titration analysis. So I know we haven't really done anything like this, but we're going to go over what titration means, how it's set up, and all the stuff that kind of goes along with it. So what a titration is, it's a common experimental design used to determine the amount concentration of substances in solution. So that is kind of their primary function is to determine concentrations of stuff. So as we have right here, we have a bunch of definitions. So a titration, the experimental procedure, where the titrant is continually added to a sample to determine the concentration of an unknown solution. So of course we have two new words here that we're just going to break down for you. So what is a titrant and what is a sample? Well, the titrant, we have definition right here, is a solution that is placed in the burette. So what a burette is, if we switch over to the next page just for a quick second, a burette is this thing right here. So it's a long cylindrical tube that comes with a little control device right here known as the stopcock that you can control the flow of the titrant that's inside of the burette, so the solution that's inside. Now the sample, normally it's the accurately known volume of solution added to an Erlenmeyer flask. So remember, the Erlenmeyer flask has a little opening and then they kind of widen as they come down. The typical chemistry flask, that's an Erlenmeyer flask. Now normally that is known concentration. Sometimes a titrant can be unknown, sometimes the sample is unknown. You just kind of have to read the question and figure out which one is which. But either way, that's going to go into our stoichiometry as either our known or our wanted substance. Now, when we're transferring stuff inside of the Erlenmeyer flask with a sample, it must be an accurately known volume. So we need to transfer it using a pipette. So this ensures that the volume is accurate. So you work with pipettes before, but you could have a volumetric or a what's the other one called? Yeah, just a volumetric pipette generally, or graduated, sorry. Those are just stuff were designed to be very accurate when transferring solutions. Now, what we have some other definitions right here. So something called an equivalence point. So this is where the volume of titrant added, where the number of moles of titrant equals the number of moles of the sample. So that is the equivalence point, hence equivalent. Now the endpoint, this is what we're going to use most of the time we're talking about titrations, is the point where the reaction is finished, and we're going to notice a distinct color change for that to happen. Now just two other things as well that showed up in our solution chemistry section, where a standard solution and primary standard. So a standard solution is a solution containing a precisely known concentration, right? So we did the video on how to make a standard solution where you accurately weigh out stuff you dissolve and everything like that. And a primary standard is what we use to create the standard solution. So it's a reagent that can be weighed easily, which it is pure. And when you use it, that means just the number of moles calculated is true. So thing is, so for the pure, we're looking at like 100% pure and stuff like that. Obviously something that's 70% pure isn't going to work as a primary standard. So, and of course standardizing, last little definition, is a process to determine the exact concentration of a solution. So basically titration, when we perform a titration analysis, we are standardizing a solution to figure out its concentration. So what we have right here is a general titration setup. So we have our burette. Inside of the burette is our titrant, and we add it into our conical or Erlenmeyer flask, and our sample's always in there as well. Now, when we're doing these titration analysis, it's not just one and done. You need to do multiple trials, and generally we try to obtain reliable results. So we keep repeating titrations until we get 3 trials that results in volumes that range within 0.2 milliliters of each other. Then we take the average of our 3 best trials and we use that for calculations. Now before we actually get into a titration, this is just a quick little demo on what a titration will kind of look like. So this is just, I found this kind of online here as just kind of a little flash simulation on what a titration will look like. So as I kind of mentioned, titration is going to happen when we reach the endpoint. We're going to notice a color change. So what we have right here inside of our burette is we have an acid. We have a base inside of a burette. Down here we have our acid. Our indicator is going to be phenolphthalein. And so what's going to happen is we're going to, add stuff until we get a permanent color change. Now, normally with titrations, you just don't dump everything in once. You add stuff. So I've done a bunch of these here, so I kind of know where to add it. So it's not going to just change color permanently. So we're going to add a bunch. So notice that pink color just kind of showed up. So this is indicating that we're close to the endpoint because we're starting to see a color change. Now, because the color disappeared, we're not done yet. So we need to keep adding our titrant until we get a permanent color change while it's stirring. So normally when we get close to the endpoint, that's when that color kind of comes out but then disappears. That's when we're going to start adding drop by drop until we get a permanent color change. So you will notice that it comes out, the color comes out, disappears. Comes out, disappears. So we're not there yet. So we keep adding drop by drop. Now, this is why titrations can sometimes take a while, because if we want to be accurate, you have to keep slowly adding drop by drop until we get a permanent color change. Now, eventually, just one drop of this titrant will permanently change the color of the solution. And so we're just going to keep going until that happens. So I know this isn't the most exciting experimental technique that you'll do, but if you're able to actually do this with your hands, you can make it go a little bit faster. Because once you do a lot of them, you start noticing that it's really close to the end. So ideally, you keep adding it until one drop will permanently change the color. Now you can tell right here the total volume of titrant being added is right out there in the corner. And of course, we use these for our calculations as well. So it's going to keep going and going. So slowly, drop by drop, until hopefully you should get a permanent color change coming out relatively soon. And boom, there we go. So one drop, we have a permanent color change in our solution, and it took 19.98 milliliters to do so. So that is what we talk about when we reach the end point. We see a permanent color change in our solution. So that indicator tells us that the reaction is done, and we would use these values here. So the total volume of our titrant added inside of calculations, depending on what information we had. So now I kind of got that little demo out of the way. Let's look at our example. So for this one right here, so a student performed a series of titrations in order to determine the concentration of KOH solutions. So KOH is going to be our wanted. So the titrant used was a 0.50 moles per liter solution of nitric acid, and the following table summarizes the student's experimental data. So this student did 3 trials. So what we have right here is the final and initial burette reading. So that means that before the titration started, the student took the burette reading to find that it read 0.35 milliliters, and when it was done, the burette read 6.58 milliliters. So to get the total, we just subtract final minus initial to get what was added. So when we subtract 0.35 from 6.58, we get 6.23 milliliters added. So we're going to do this for all the trials. So for trial 2, the student added 5.22 milliliters. For trial 3, the student added 5.15 milliliters. And finally, for trial 4, the student added 5.20 milliliters. Now, when we go back to our previous page here, it said that we get 3 trials that were results within a range of 0.2 milliliters of each other. So that just means that, we kind of narrow in on the most precise there. So when we look at the values, we can tell that our trials 2, 3, and 4, so we had 5.2, 5.1, 5.2. So these here fall within 0.2 milliliters of each other, which means this one right here, so this one's almost an entire milliliter off from all the other trials, so we're going to omit this bit of information because it is not used. Now also, if you go back and read a little bit more, the results, the 3 results that we choose are then averaged to get the total volume or the average volume. So we are going to get the average right here for these here. And remember, this is for nitric acid. So in order to get the volume, you just add them up and divide by 3. So we got 5.22 plus 5.15 plus 5.20 all over 3. And we get the average of 5.19 milliliters. So this is going to be used at some point, because we're not going to do 3 different calculations for this, right? We're just going to get the average. So, and now, based on that, we know the concentration of nitric acid. Now we have the average volume of nitric acid. So we have all the information we need. Now we can go off and do our 4 steps of stoichiometry to solve the question. So first of all, calculate the concentration of KOH, solution when 10 milliliter samples are used. So first of all, we need to know our equation. So we have nitric acid plus potassium hydroxide. This is an acid-base neutralization reaction where we get our salt and then plus water. And make sure to balance, which in this case right here, it is already balanced. And we highlight this is given and this is wanted. Obviously it's wanted because this is calculate the concentration of KOH. And of course up here we have our titrant. So I know there's a lot of numbers for these right here, but this is why we kind of just have our average volume right here. We know the concentration, and here is the volume of KOH. So you can kind of write down all the stuff between wanted and given if you want to kind of simplify the things, or you can just kind of go back and refer to the question and get the numbers when you want. So second step in stoichiometry is always find the number of moles you're given, and because we have concentrations and volume, so we have number of moles that are given is C times V. So when we go back and reread the question, right, we have the concentration of our titrant is 0.50 moles per liter. So that's 0.50 moles per liter. Now the volume we have right here. It's the average volume of the nitric acid. So we're going to use this. So 5.19 milliliters. Of course, we can't use milliliters with concentration. We have to get that into liters. And it's 0.00519 liters because we divide by 1,000. And we get number of moles of 0.002595 moles. Then we move on to step 3. Number of moles are wanted is equal to number of moles are given times our mole ratio. So we take our 0.002595 moles and we multiply by wanted 1 over given 1. And we have our exact same number. Finally, step 4 in stoichiometry, solve the problem. So the problem is concentration of our wanted, or KOH. Remember, the formula for concentration is number of moles divided by volume. So number of moles we just calculated in step 3 over the volume. So once again, what is the volume of KOH? We go back and reread the question where it says calculate the concentration of KOH solution when 10 milliliters of the sample are used. So 10 milliliters in liters is 0.0100 liters, and we get a 0.2595 moles per liter, or for significant digit wise, when we start looking through, we got 2 significant digits up here. These here, 3 significant digits, 3 significant digits. Obviously 2 is the lower one. So we answer our question with 0.26 moles per liter. And that is it for the calculations. So you'll notice very, very, very similar to our stoichiometry problems, because essentially these are stoichiometry problems. The only difference right now is using the experimental data. But remember, all titration questions, specifically if you're given the multiple trials, you're using three of, I guess, the three closest values. So I'm going to go over example 2 with you guys and let you do example 3 kind of on your own. So let's look at another different titration example. So for this one, if we read carefully, we see students need to know the concentration of a sodium chloride solution. So obviously sodium chloride is going to be our wanted thing. So we have 50 milliliter samples of sodium chloride. Okay, so we know this is part of our wanted. Solution are titrated with a 0.500 moles per liter solution of potassium nitrate. So this should be our given, because obviously if sodium chloride is our wanted, our next thing, our potassium nitrate solution, is our given. So that means if this is our titrant, our volume added is for the potassium nitrate. And sorry for that showing up there. So the indicator below is a bromothal blue solution. I don't know why this is an acid-base one, because this is an acid-base indicator, but either way, this is the information we have, so let's run with it. So first step is let's figure out the volume added of our potassium nitrate, or our given solution. So we're going to go through the same steps before as we subtract the initial reading from our final. So for our first trial, we added, or the students added 9.0 milliliters. Our second trial, they added 11.5 milliliters. The third trial, they added 8.9 milliliters. The fourth trial, 10.1 milliliters. And finally, the last trial, 9.1 milliliters. So remember, we want 3 trials that fall within 0.2 milliliters of each other. So just by looking at 9.0 to 8.9, that's 0.1 from each other. 9.0 to 9.1, also 0.1 from each other. So we have trials 1, 3, and 5 fall within that range. So that means we are going to omit trial 2 because it doesn't fall within our range. And we're also going to omit trial 4. So we're going to use this one, and this one. So, same thing, V average is equal to 9.0 plus 8.9 plus 9.1 all over 3, and we get an average of 9.0 milliliters of KNO3 added. Cool. Now that we have all of our information that we need, so we know what our want is, we know our given, we have the average volume of our titrant. Now we can go through our 4 steps of stoichiometry to solve the question, right? So step 1, balance chemical equation. Well, we have our potassium nitrate solution reacting with our sodium chloride solution, a double replacement reaction. So we're going to get potassium chloride solution, and of course our sodium nitrate. And we know from reading the first part, our sodium chloride is our wanted, whereas our potassium nitrate is our given. So next step, 2, number of moles of our given is equal to C times V. So the concentration up above, we had a 0.500 moles per liter solution of our potassium nitrate, and on average we used 9 milliliters, so that into liters we divide by 1000, get 0.0090 liters, and we get the total number of moles of 0.004 moles. Step 3, find the number of moles of our wanted is equal to the number of moles of our given times our mole ratio. So we take our 0.0045 moles, multiplied by our mole ratio, wanted, 1 over given 1. And we get 0.0045 moles. And last but not least, step 4, solve. And if you read the question, it is what is the concentration? So the formula for concentration is equal to number of moles divided by our volume. Our number of moles we just calculated. The volume up above is said it was 50 milliliter sample, so of course 50 milliliters in liters. We divide that by 1,000 to get 0.0500 liters, and we get an answer of 0.090 moles per liter, and of course that is 2 significant digits. We're using 2 significant digits because of the 2 significant digits in our 9.0 liters or milliliters for our titration. And that is another question, kind of setting up, making sure you get all the information first, and then once you have all your informations, your volumes, your concentrations, you start going through your 4-step method to solve stoichiometry problems. Now the last one is 3. Now this one isn't one of those trials that have multiple. This one is just reading it, see if you can figure everything out on your own. But when you do, what is the concentration of HNO3? Please do this one. You should a concentration is equal to 0.1926 moles per liter. And work on this one until you get it. Of course, if you don't, just let me know and we can set up a Google Meet and I can fire this one off for you, or I can do this one and send you a screen capture of what the answer looks like, or you can hop on to the Google Classroom, look at the answer key for the notes and see this one fully worked out for you. And that is it for titration analysis. So our last video for this entire unit and for all of Chem 20 is going to be on titration curves. So what would happen if we actually graph this? There's going to be no calculations for it. It's just going to be a theoretical kind of thing that is nice to know, especially if you plan on doing Chem 30, because we see these curves show up in Chem 30. All right, so one more to go. I'll see you guys for the last lesson of Chem 20.